Hello folks, I'm back with another exploration into the world of C. Now, I'm not a full-time C developer by any means. I learned it like 20 years ago. I've dabbled since then. Never really built anything super useful, so I'm going to try and change that now, and that's part of what we're going to be looking at today. I have no idea if it's going to be a one-off or a multi-part series. It just depends how productive I am and how well I do. So what I want to do is I really want to play with serverless functions. And you might think, well, what's that got to do with C? Well, I want to test the performance of different serverless functions. So if I write a serverless function on AWS Lambda in, let's say, C++, Go, Ruby, I want to see what the different cold start times are to run those functions, essentially. Now, you could say, okay, that's fine. You can go and use an existing benchmarking tool to make the HTTP request, measure the time, and so on. But I've always had trouble with HTTP benchmarking tools. Like, they're never entirely transparent about how they work to me. I mean, you know, you're going to probably recommend one that's really good, but I kind of want to get loads of things out of the way. I don't want to worry about DNS. I don't want to worry about caching. I don't want to worry about like any of that. So I literally want to give it an IP address, the host name that I'm trying to connect to, the path and everything, and then get time measurements of every single part of the process of making a single request. I don't need to fire out hundreds of requests or anything like that. It's like very simple, literally just does a raw connection. But I mean, just to get some of this in my mind, I'm going to start drawing a little bit of this out. So let's say I've got my HTTP server here, and I've got my program, which I'm going to call HTTP test. I basically just want to call it myself as me. Here's me. I want it to make a single connection and to measure on a clock the time between triggering it and then the correct result coming back. And I want to know that to whatever the finest granularity is that I could possibly know that. Now I thought, well, I could easily write something like that in Ruby. Like, that would be super easy for me. I'm quite proficient with Ruby. But Ruby takes a while to load, which actually isn't a big problem if you're measuring the time correctly once you actually start the HTTP request. But there's things like garbage collection, and Ruby runs at a certain speed and so on and so forth, that I thought I don't really want to use an interpreted language for this. So let's use something a bit more kind of performant. I thought, well, I could use Go. But then I thought, well, since I'm trying to learn and C again anyway, let's use C and let's do it really at as much of a raw level as I can without moving to assembly language. And so that's where I'm at. So what I've done is I've created a empty directory called HTTP test, and then I've created two very simple files in it. So the HTTP test.cc file, and I'm writing in C at the moment, even though I'm kind of treating it like C++. I just bring in the standard I/O header. That just allows me to use printf, and I'm just printing hello world to the screen. Really simple stuff. So if I come in here and I just do this type of thing, in fact, actually, I don't even going to put an output. I'm just literally going to go like that. That creates my a.out, and then it gives me my hello world. Easy peasy. Thing is, when you're working with C a lot, generally you want to move to using makefiles or some kind of build process that handles a lot of the complications of the build for you, so that as you get, this G++ is very simple, but as it gets more complex, as you start adding things like standard declarations onto it and doing output files and then adding more files in, doing linking, all that type of thing, it gets more complex. So people build what are called makefiles. Now, most C or C++ based software in the Unix world has a makefile in it somewhere or another. So here's a very basic one that I've made. Let me just quickly explain what this does. So what make does is it will run the first kind of one of these declarations it finds, which are essentially dependencies within the makefile. And all I'm going to do is I'm going to run G++, run it with the C++ 17 standard just to be super modern, output to HTTP test, which is my executable, and then the source code is http test.cc. I've also had a couple of other tasks. These are not run by default. These are only run if I type make clean or make install, as you can see here. And what happens with clean is it just deletes the executable, so it just cleans stuff up. Most programs would have this delete object files and various other sort of artifacts of the build process, but I have none other than the executable, so that's easy. And my install installs HTTP test into user local bin. Now the way this works is I create variables up here with this information in so that this can actually be overridden at the command line if I want to change the prefix of where something is put. If it's not into user local, it's just user or something like that, I could override that. So that's what this question mark equals is. It's like if this is nil already, then put user local in it. Bin just takes that prefix and adds bin to the end, and then install just refers to the install command, which is common to I think all Unix distributions as far as I know. I'm not too sure, but all it does is it just copies a file from one place to another and makes it executable, so you'd have to do the chmod plus x and all that type of stuff. So if I give this a test, I just run make, I now have my program, and if I go make install, it puts into user local bin, and so then even if I'm somewhere else on the system, probably not there actually, it's probably the worst place to do it, it works. Hello world. Let's head back into that directory. So I basically want to, I'm going to run make clean to get rid of this artifact, which we don't want there. Cool. So there's a few things I want to do here. Now I'm going to keep this program really, really simple, and especially for this first episode, I think I'm going to break this up into different episodes. But it's a few things I want to do, and ultimately you'd think what I'm going to want to do is I'm going to want to take command line arguments for IP address, actually I've just realised there's a bit of a complication to this because I can't just open raw sockets to things because of HTTPS. Maybe I'll just build the first version just using raw HTTP, but then I'll need to extend it with all the features for HTTPS, so yeah, that would definitely be a future episode. But let's start with just HTTP for now. So we can give it the IP address, the port we'll just assume is 80, we're not going to worry too much about that. Is there anything else? Oh yeah, and host name. So at this point we'll have the IP address and the host name. For now, I think we'll just fix them by hand. Now I just need to find an HTTP server I can test this against. Maybe even, yeah, okay, I'll need to find an HTTP server, so that's one of my next tasks to do. What could I do that's not going to kind of annoy anyone too much? I'm not sure. Let's move on to what the next step of this is going to be. So once I've got an IP address and a host name, I've got my port number, which I'm actually going to put in here. There you go, declared an integer, port 80. The next thing to do is, let's just guess, open a socket to IP address and port. Once connected, we're going to send a basic HTTP request, which will involve the headers and the get and all that type of stuff. Oh, there's actually a couple of other things I'm going to do. I am going to, at this point, start a timer or kind of record the time in some way. We need to see how it's going to work because I have no idea I'm going to do that. And I guess at the end we're going to print results, and we're also going to stop the timer. Good. Once connected, send basic HTTP request. To do wait for HTTP response. To do check HTTP response is correct. So that's whatever we expect it to be. I think initially we'll just make sure it's 200. If it's 200, okay, fine, we'll go with it. Keep it really easy so we don't have to check for any particular string or anything like that. Right. So there's a couple of bits of this I can bite off kind of straight away that are reasonably easy, I hope, which is going to be starting a timer, recording the time, and then printing the results at the end. So what we're going to do is so just to demonstrate here, hopefully this will put in a floating point number in here. I just realised it's not F, is it? Or is it? I can't remember. Let's find out. Oh no, that works. I just know there are different ways you can extend this formatting on this. Hopefully we'll get it in milliseconds, actually. Let's just make this easier. Will that work? Why is it up to date? Oh, it's because the file already exists, that's why. So we need to go make clean, make, and then run HTTP test. Okay, perfect. I don't know whether we'll end up using a floating point for this or just literally, because milliseconds are pretty precise already, aren't they? We don't need 2.5 milliseconds. So this could well become something along these lines. And then what I'm going to do is I'm going to actually speed this process up. Cool. 5 milliseconds, right. Let's go and find out, and this is where I'm going to start hitting Google, how to accurately measure, not body fat, time in C. Okay, let's have a look at some of this stuff. I don't want to get too bogged down in science here. What have we got here? Clock function that's in time.h. Okay, this looks like the simplest place to start. Let's give this a go. So we've got time.h. What's the type it's using? A type of clock T. Which is probably just some kind of... Oh, hello. Great, thanks. We didn't want that. What we're going to do is we're actually going to steal this code because this doesn't look too bad. Okay. And that is using a double, so that is a floating point number there. Let's put the port there. Let's call that timer start and timer end. And it says CPU time passed. I hope it's going to be wall clock actually, so that might be something I need to look into. Let's have a look. Clock function, we'll have to get processor time. I get the impression this might actually be wall clock time and not actually CPU time in the Unix sense. I guess we'll find out. Here we go. So start the timer is going to happen there. And then we've got another one for timer end. Do the work, we get rid of that. Stop the timer there. CPU time used. So, okay, I think I'm just going to do time passed on that. Okay, time passed equals timer end, my timer start, clocks per sec. Oh, okay, so clock is returning like ticks of the CPU or something along those lines. I'm not quite sure. What we're going to do though is let's find out what is actually going on here. Okay, that's a start, but I don't actually know what's going on. What I'm going to do is between these two clock calls, I'm actually going to put a sleep in. Now this is what I need to remember, something like how to sleep a C program. And this is how a lot of people program, isn't it? You just search for stuff. Oh, there's different ways of doing this on different platforms. So this brings me to another point of C, which I never had to work with before in the past, but is now going to become relevant, which is you can set up these, you can use definitions to include certain bits of code in certain situations. So you can say, like, if we're running on the Windows 32 platform, then do this, and if we're running elsewhere, then do this. It's because Unix and Windows have different ways in C of measuring, of doing the sleep process, essentially. I don't want to target Windows at the moment. This could be something for the future I need to worry about. I'm not going to worry about it for now. I will follow the Unixy way of doing it. And then it's just literally use sleep. Easy. Cool. Pull that in. I'm guessing if it's use sleep, is that microseconds? So let's pretend this waiting for HTTP response is this section. Use seconds. I'm guessing it's microseconds. Let's have a look. 100 milliseconds. 100,000 milli. Yeah, million. Okay, right. So in that case, that should get us a second then, shouldn't it? Okay, so I'm not entirely sure what this number is. Let's make it 3 seconds. This doesn't seem particularly accurate, does it? Ooh. So maybe it is CPU time, you know. That's not what I want. Because now look, it's coming up with the same result whether I did 1 second or 3 seconds. That's because it's not using the CPU during that time. So it's obviously measuring CPU time. I don't want that. So to accurately measure, let's call it wall clock, because that's often what this is referred to. Yeah, here we go. Here's a copy-paste solution. I bet this has been used in about 50 different code bases. Right, again, it's worrying about Windows, which I don't care about. Okay, so there's a different function here. Get time of day. Yes, so that's wall time, and then CPU time is clock. How accurate is this get wall time, though? Okay. Let's see how far we can get with this. So we've still already got time in there. Let's just see if this works. Time end. Okay. Yes, there can be errors. I'm not going to worry about the errors. Yeah, this is all going to be different, isn't it? Time end. Oh, hang on. This doesn't work how I thought it worked. I'm going to ignore the results, because the results are just whether it succeeded or not, I'm guessing. So we've got time start, time end. Let's give it a more interesting length of time to pause for, that, so that we basically want to find out 1.2 seconds. That's what we want to find out. So we'll actually be testing how accurate this use sleep thing is. So we're going to get the time of day, start at the time of day, and let's just make sure this works as is for now. Right, yeah, time pass doesn't exist yet, so how do we use that? Get wall time. Return double. Time dot TV sec. TV microseconds. Times. Okay, that makes sense. That makes basic sense. Oh man. Let's do it this way. Let's make this just time measurement. It's kind of almost like a temporary variable, essentially. And then what we'll do is we'll turn that into time start and time end. Like so. So it just takes the number of seconds and then the number of microseconds and then multiplies that by the correct kind of amounts, turn it into an absolute number, absolute value. So what I'm going to do is, rather than create a function at the moment, I'm just going to do that. And so we should be able to take the end time, delete the start time, and that will give us our time difference. Got a problem. Undefined get time of day. I'm guessing that's to do with the other header file. I keep going the wrong direction there. Is it this one? Now, this is one thing I don't quite understand what the difference is. So it will be interesting to find that out as I go along. Here we go. Perfect. So we're sleeping for 1.2 seconds, and we're getting the 1.2 here. It's not milliseconds, it is actually seconds. If I go like that, and then I go 1,000, that's it. That's perfect. So 1,200 milliseconds, 0.04, blah, 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 because that's just, you know, the machine's doing other stuff. It's recording this video and so forth. So, cool. Okay. Let's just double check that just to make sure. That should be pretty close to 1,000. Oh, ooh, hang on. There we go. Yeah, there's a stray few milliseconds creeping in here and there. That's kind of interesting. It's not actually that consistent. I mean, it's pretty intense recording this video, but still, that's a couple of milliseconds creeping in there. Okay. Might want to look into how accurate U-sleep is in this case, because I don't know much about its accuracy. Again, this isn't something that's going to worry too much. For accurate times, get time of day is accurate to about a microsecond, so that's fine. Microsecond is totally fine for network stuff, at least at this level. Guarantees to wait at least as long as you tell it to until... Okay. Well, it seems like U-sleep's pretty good. We're not too worried about the sleep. This is literally just for test purposes, so let's not dwell too long on that. So we've got a port, we've got a time measurement, blah, 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 we've got a time difference. Let's now break this out into a function just to... make my life a little bit easier. So then what we can do is we can take the declaration of that, and then I think we've got a function on the go here. So it will be a double, what was it, get current time, da. Yeah, that seems fine. Stop the timer, time end. Perfect. What we can now do is change these, so they're not to do anymore. Now there is a Visual Studio Code extension that will apparently change the color of lines. If it's a to-do, it will make it kind of red to do and, you know, green when it's done and stuff like that. I've not got it installed yet, but I've seen a lot of people recommending it, so I want to try that out. It's kind of a note to self there. So we've got the port, blah, 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 we've got the time. Right, I guess we're going to have to worry about the socket next, because we've pretty much got what I was hoping for there. Perfect. Okay, let's have a look. Actually, I've just thought of a good example. Example.com. This is set up for by one of like the internet. Is it the Internet Engineering Task Force or someone like that? No, the IANA have example.com so because it gets used in examples, and so they host this, and it's always on port 80. So if you need something on port 80, you can kind of rely upon that. So there we go, really simple. Now if I test, if I test going to port 80 on that, perfect. Oh, hang on. It's because I haven't put the host name in, that's why I've just done HTTP 1.0. This is me writing HTTP directly over the wire, so... Whoops. Ugh, why am I so bad at this? There we go. And it's obviously doing keep alive, that's why it hasn't stopped at the end. Perfect, right. This is what we're going to do. We're literally going to do this very same thing that I just did here, but in C. So, we don't actually want to do that. The next thing we want to do is open that socket to the IP address and the port. So I think for this video we can probably bite these two things off, which is, oh, actually we do print the results, that's kind of done. Let's have a look. So, example.com, I actually want to basically look that up in advance and get the IP address. We don't want to add IP DNS to this program, at least not yet. So that's that. And what's the next thing we need? Oh, path would just be nothing, basically, just be the root kind of document. And last but not least, what have we got? In fact, let's bring these things together. Char path, char host. I'm missing something, aren't I? What is it that I'm missing? My mind's going blank now. Got too many things going on. Oh, it's the host name, of course. So this is example.com. I think those are all the things that we need. I'm just going to keep testing the program to make sure it still works while we're here. That's perfect. Going to get rid of this sleep now because we don't need that anymore. So, how do we open a socket? Now, this is quite complex from what I... Let's go and have a quick look. I don't know why, if I see .edu, I kind of think, yes, it's going to be nicer for me to use. Server code, right, I'm going to need a bunch of things. I need to include a header file for some types and socket.h as well, because basically I'm going to be opening a raw socket, so that makes sense. Constants and structures needed for internet domain addresses. Okay, we'll take that as well. Int main, right, sock fd, new sock fd are file descriptors. They contain things returned by the socket system call and the accept system call. That makes sense. Port number stores the port number. We've already got that one. Client stores the address of the client. Okay. N is a return value for the read and write calls. It contains the number of characters read or written. There's a buffer. Read characters from the socket connection into this buffer. We're going to need one of them. There's a struct. Sock adder in. It's a structure containing an internet address. Here's the definition. Family, port number, the address. I'm guessing this is some sort of padding. Okay. Socket, right, okay, so sock FD. Let's start with that. In fact, let's just start with this whole piece of code here. Let's just start with this. So, this is just getting hold of a socket. Sock FD equals socket, AF internet, sock stream. That's for TCP rather than UDP, I believe. This is under 0, then raise an error about opening the socket. Okay. Let's just give this a try. Okay, there's no such thing as error. I didn't think I recognised that. Oh, okay, so they've created this little function that just raises an error and quits, basically. That's probably a good idea to have. We'll have one of them as well. We'll just copy that, and I don't like this formatting of the braces. It's more common in GNU code, is it not, to put it on the next line? I like it on this line. This is how I learned to do it, and I just think it looks nicer. P error. I have no idea what that is. What's P error? Let's quickly look that up. Prints a descriptive error message. Ooh. That's a good point. Yeah, when you're passing a string like that, it will come across as... Need to look into that as well. It's passing a string across, and we need to handle it in a slightly different way. I know what we'll do. Let's just do this by hand for now. No. We should want to do it this way, yeah. Same as the one up there. Try that. What? Things have changed since the DOS days. Okay, that seems to work. Let me look into that, actually. So this is probably quite an old article. Linux, terminate the calling process. Close file descriptors. Seems fair enough to me. Ah, that's why it's in standard lib, okay. Does not call any functions. Okay, so that's more extreme. What I actually want is to do that. Whoa, okay. That's flying around a little bit. And then just use normal exit. There we go, perfect, right. So we've got the socket started. Now's the actual hard work. I probably shouldn't be following such an old article here, actually. Oh, this is the server code. This isn't even the client. Oh, let's go to the client. Okay, this is all the same sort of stuff though. Get host by name. That's basically a DNS lookup. We don't need that. This is where it's populating basically the data structure for the information about the port and everything. And then there's the actual connection taking place here. Okay, so we definitely need one of these, because this is our data structure that stores information about what server we're going to connect to. And we definitely need one of these. It's interesting they don't close off the connection again. Fair enough. We won't worry about that until later either. So, connect sock fd, blah, 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 blah. And then what we'll do is we'll just rip off what we did before. Error connecting to server. Like so. Of course, nothing's actually going to work yet because I've not got this serve adder thing going. And we should see that when we try and compile. Of course, it finds a completely different problem. There we go. That's because, actually, sorry, we do have serve adder server address. We just haven't populated it with anything. So it's trying to connect to nothing essentially, which it's failing as we would expect. So that's good, I guess. Now we just need to populate it. That's going to be the fun part. Let's see. So this B copy is because it's copying in things that are pointed, things that are pointed to, not like sort of literal data. We've got everything as literal data, so we might not have to do it this way. Actually, no, we will with the strings. Ugh. Okay, there's a few things here we can copy. Let's have a quick look up. I want to just double check what these B0 and B copy things are, if they're actually modern C or not. Because, yeah, I'm more used to seeing memset and memcopy. They're not ISO C. They were a POSIX standard. They predated blah, 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 blah. They were deprecated. Oh, they're old-fashioned. Right, okay, memset, memcopy. So I'm literally looking at a really old article here. Kind of like it, though, because it's kind of cool to learn about these differences. What's the difference, then? Mem move is completely back to front. Okay. Okay. So what have we got here? I'm actually not going to worry about this. That one's fine because that's just saying it's an IP. It's an internet address, basically an IP, kind of connection. So that's fine. What other things have we got in that struct? We've got the actual address. We've got length. Whoops, I didn't actually want that. That needs to equal something. And port needs to equal something. I'm hoping that can just equal the same as our port here. I need to know what this structure is like. Is it possible to look this up? It is. So here we go. It's gone to the actual header files on the system, and it's going to show me what's in them. Import T is a 16-bit integer, which makes sense because port numbers can be between, I can't remember if they include 0 or not, but definitely between 1 and 65,536. So what we'll do is in underscore port underscore T, okay. We'll do it like that, because then we can just assign port to it, that's fine. Let's have another look. What else have we got? That length is an 8-bit integer. I'm not sure what that is. That's another struct. And then that's just padding on the end, I think. Alright, what was this length thing all about? Server length. It's like H length. What's H length? I have no idea. It's basically like the length of itself. Who knows? I've just realised it's getting quite dark here, so it might be quite hard to see on camera. And what's this H2NS? H-tons. Let's look that up. From host byte order to network byte order. Ah, okay, that makes sense. That's probably a good thing for us to do, actually. Yeah, let's do that. Whoops. Because the endianness essentially can be different. Which way round the bytes are within the integer there. Can be round the wrong way. So let's get them into network order. So we just need to do this address thing and the length thing, and the address is another struct, annoyingly. So I need to learn how to populate that. How are they doing it here? What's this host ent? I think it's because it's doing a DNS lookup. I actually don't want to do it that way. Let's go and look up a different tutorial. It might be a bit more modern. This is a server. Let's just do this. TCP client. Again, yet another old website. Client program which acts as the parameter of the server name tries to send data to the server. Based on BJ's program. I've heard of them before. Connect their address. I've got the family, I've got the port. 0 the rest of the struct. Interesting. This is also old because it's using that B0. They're using get host by name as well. What does that actually return? Get host by name. Returns this host nth thing. What's... Oh god, it's all modernised. Ugh. This is all old stuff. And this is, I guess, a problem with C. Okay, they're putting a... Oh, okay, this might be more up my street. Server address, 0. Interesting. What does this do? Converts an internet address in its standard text format into its numeric binary form. So it'll take like 1.2.3.4 and turn it into, yeah, just a single 32-bit number. That is what I need. And I'm going to ignore the response from that. Okay. I'm also going to try this thing that they've done at the top there. I'm wondering if that zeroes it out. Who knows? I'll find out. So we'll populate it in this way. So address will actually be the host. So that gives me that. And then we've got this length thing. What's he doing about that? Or she. I have no idea who wrote this. They don't seem to be worrying about it. Let's not worry about it. Let's just comment it out just in case. So we don't need this section anymore. Oh, look, they've done it already there, look. Okay. Connect, sock, FD. What are they doing? Connect. Description, struct, sock adder. Size of. Perfect. Let's just save that and compile, see what happens. Undeclared identifier, inet p2n. Guessing that comes actually in the ARPA inet headers. It does, and there's no errors. So I believe it has now connected to example.com successfully, because it's passed through here and it's done the timing thing. So we actually have a win. What we'll also do is I'm going to steal the thing for closing, and actually I'll get rid of that entirely now. Stop the timer. There we go. Close socket. We'll do it after getting the time so that it doesn't influence anything. Where is our socket file descriptor? It's there. Yeah, we'll just click. We won't check for errors at the moment. Perfect. Okay, so the next thing I want to do, just to make this video actually useful, is oh, actually, we want to start the timer before we do the connection. So we'll literally start the timer here. Connect to the remote server here. Create the socket here to use to connect to the HTTP server. And that's what we do. In fact, I'll just do that. Blah, 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 blah. So there's an error. It builds it all together. I have no idea what that's all about. We don't need that. Start a timer. Record the time. Connect to the remote server, which it does successfully here. This is the bit where then I'd send the HTTP request and look for the response. We stop the timer, close the socket, print the time. Aha, so here we go. We can actually see now how long it takes to make the HTTP connection without even like issuing the request or anything. And I could actually measure separate things here, you know. This could be interesting. So for example, let's say I don't want to just measure this. I want to measure the connection time. Let's have a look. What I'm going to do... Oh, actually, I don't need a connect start and a connect end. All I need is a connect end. Because I'm already measuring the time at the start. This is the connect end time. Like so. And then we just need the connect time difference, which I don't want to calculate in the middle of this routine. I want to do it right at the end. So what we need is connect end and minus times start times 1,000. Oh, what have I got wrong? Oh, connect time difference. In fact, what I'm going to do is I'm going to bump these down to the next line and just do it this way, just to make it a bit cleaner for me. So there you go. Now we can see how long it took to connect to the server and then how long it took overall. So currently those numbers are pretty much the same because we're not doing anything. Now we actually need to send the HTTP request. Let's go back to that file from before. Minimal TCP client. Oh, this is the one we were on before. Sorry if this is hard to watch on the video. So we connect. We could go forward with read and write calls. Oh, shutdown. Maybe we should be using this rather than just closing the socket. Okay, I'm guessing that just connects and disconnects in a much cleaner way. So we can use read and write calls. Okay, let's look that up. So GCP write. Let's just click on the first thing we find. Client.c. Oh, hang on, we've seen this code before, haven't we? We pass in a buffer and the length of the buffer. Okay. This is going to get a bit more interesting. We're going to create something to store our return values in. Printf. Can't write to sockets. Actually, can't write to HTTP server. Right, so we've got our file descriptor, but it's called sockfd, that's correct. Buffer, which is what our string is going to be in, and then the length of that buffer. So str_len gets the length of a string. Okay. Get keep track time it took to connect to server. Right, send basic HTTP request. So, what's the best way of doing this? Is it something along these lines? This is where I'm going to start grimacing a bit now, because this is where I get a little bit rusty with some of the syntax. Now, I can't remember if it's just NN or if it's like when I'm doing an HTTP request. Is it new line and return or just new line? Which break line is for RN or just N? RN. Okay. The line terminator for message header fields. Carriage return line feed. Okay. So what we'll do is just to be fully correct. I think you just do 2 to get that going there. Hopefully this will allocate this onto the stack and not... What's the error squiggle? Expected for aggregate object. I've got this wrong, haven't I? Something like that. Ah, there's no string length. Oh man, I've really messed this up. Ugh. It's in string.h. Can't believe we haven't got that yet. Ugh. Oh, it's not an array, is it? Hang on. ISO C+11 does not allow conversion from string literal to... Okay. Let's just try this. Okay, that works. This is where I get in some of the things to do with allocating memory and pointers and all that stuff mixed up. Must admit, I'm starting to flag on this video now, so I probably will bring it to an end very shortly. But that should actually be issuing it, and it's not coming up with an error, so that's good. Let's immediately move into doing the response, and then we can do another video about cleaning it up, and then eventually getting onto HTTPS as well. So, the read is the other way round, and we can create a little buffer for that. And I only want to read like the first small bit of the response anyway, so I don't actually want to worry too much about things. Okay, yeah, we'll print out the response as well. Actually, I need to do quite a few changes to this actually. I can also pass that host. I'm already passing in the host. Okay, this is where I'm flagging. Right, so wait for HTTP response. What we want is return value. Return value is on 0. Then we're going to steal this piece of code here. Can't read from the HTTP server. It's only going to read up to 255 bytes. Do assault D. It's going to put it into buffer. Perfect. And then we're going to print out what actually comes back. Interesting. Let's do that. Whoa, that didn't work. Oh, we've already got a buffer. Hang on. Let's do that. So we already had buffer defined. We were trying to define it again up here. We can only have it once, so I've changed this one to HTTP request. Aha, here we go. So it has read the response. It actually works perfectly. And we have our 200 OK here. Awesome. I think there's a bunch of reasons why you might not want to treat a 200 OK as being the be-all and end-all. I'm going to treat it as that here, but you might not want to if it might be a situation where the remote server is intelligent and it will reply with something that's okay, but perhaps still being constructed at the server end. So if you had a function that was running, it could well still be running and trying to produce output while the HTTP server, the endpoint, is essentially saying, yes, this is okay, let's get this out, but it's still producing the other stuff behind the scenes. So you might want to actually get the whole response back before you actually verify if it's correct or not. So I don't know if I'm going to make the right decision here. For now, all I'm going to do, just to keep this video at a decent length, is I'm now going to treat this response as being legitimate, essentially. If it's over a certain length. We're not even going to look for the HTTPS code, the HTTP status code at this point. What I am going to do is I'm going to... In fact, I've just realised I think the return value is actually the number of bytes it's read. So they might be the same. Yeah, 255, 255. So what I'm going to do is... I'm actually going to reduce this because there's probably HTTP servers that would send a shorter response that's legitimate. So this is where we're going to check if it's fine. And it's not HTTP status 200 for now. It is so what we're going to do is get rid of that. And then we're going to say if return is not equal to 64, then we're just going to say it's not as expected. Actually, let's structure this around the other way. It's more logical. HTTP response is fine. Stop the timer. To be honest, we should actually be stopping the timer immediately after the read and before we check the validity of the response. Perfect. Let's just quickly walk through this again. So we've got all our header inclusions here. We've got our function getCurrentTime, which gets the current time and then turns it into a number that is a number of seconds, essentially. We've got our main function here, our return value thing here. We've got a buffer for the response from the HTTP server. We've got the port number, we've got the host name, we've got the path. We're not using the path yet, and we're not using the host name either. They become relevant in the HTTP GET request. We need to kind of interpolate those in. I'm not going to do that in this video. This is our server address. These are all our variables for storing the time information. We don't currently pass the command line arguments to get this stuff on the command line, but we will do. That's another video. We create the socket. We populate the server address struct. We start a timer. We connect to the server. We keep track of the time it took to connect. Then once we are connected, we issue an HTTP request. This is where we need to interpolate in the path and the host name. We write that stuff out. We could actually measure the time that it took to write stuff out as well, potentially. It's not super useful. We could. Then we wait for the response. That's no longer a to-do. We've actually done it. We stop the timer. Then we check if it's okay. We say whether it's okay or not. We shut down the socket, and then we print out the results. And there we go. So it's taking around 90 milliseconds to actually connect to the remote server, and then the actual response is taking another 80 to 90 milliseconds. We could calculate the difference between these two just to get that number, but yeah, okay, that's roughly how long. And if we just do a ping, let's just see how slow it is compared to the actual ping time. I guess that makes sense then. So example.com is actually about 90 milliseconds away from me, so it's not really a surprise that it takes 90 milliseconds to connect and then another 90 milliseconds for the response. Kind of all makes sense, to be fair. Cool. So it's actually example.com. You're doing a really good job of responding very quickly to my requests. So I'm going to cut it short for now because this has gone on quite a long time and I have to get home. But I hope you've enjoyed that. I've kind of learnt a few things doing it. And yeah, looking forward to extend this in a future episode and sort of find out how to get some of these other things working, like the string interpolation, which has completely gone out my head how to do that. And actually pull out the HTTP status code. And, of course, also doing the HTTPS SSL stuff, which is going to be proper over my head, I suspect. But we'll figure it out. We'll get there. We've come a long way just in this one video, so thanks for watching. Hope you got some value out of this. Leave all the comments you want, subscribe to my channel, all that type of stuff, and see you soon.